Okay. Today we will study 14.6. Directional derivatives. And gradient vector. We have learned what is partial derivative, say given the function x, y. Right, the partial derivative along x direction means we fix y and assume x is a variable. If we take derivative along y direction, then you take a derivative as a function of y with x fixed. But if you plot the function you will see a surface, right? So if you look at the x direction, you will get this curve, you get a slope, which is the fx, and this slope will be f of y. But x and y are just the two special directions. You can take a derivative along other direction. For example, if you follow the diagonal here, then you will see a curve like that. Right? You know, this is the curve where x equals y. So you can also ask about the slope in this direction. And you can also ask other directions. So it seems there are intermediate choices, but they are not independent. For example, if I ask you what is the slope along the diagonal between x and y, you can find out it's actually depending on these two numbers. It's determined by these two numbers. So these two numbers, the x derivative and the y derivative, tells you the direction along every direction, the slope along every direction. The reason is, if I know the two slopes along x and y, then I know locally it's like a tangent plane, right? There's something like that. So if I ask you what is the slope in this direction, x, y, no, right? If I ask you what slope along the diagonal, you can also figure out from these two. And any other direction can be figured out, right? And in particular, there will be a direction where it's horizontal, which means the slope is 0, right? And there is another particular direction where you have the steepest ascending or descending for object way, right? Like in a mountain, right? You can always find a direction where you are going along the contour line, you know, not going up, not going down, right? So let's talk about these things today. Suppose I ask you to find a derivative along a particular direction. Let's say derivative along a particular direction, along, let's call it v. In this case, v will be a two-component vector. Let's say, let me call it a and b. Okay. Then what is the derivative along v? It can be written in this way: d sub v. F then is defined as a times fx plus v times fy. Well, that's a definition, but this definition has a geometrical meaning. Let's take a look at the simplest example. AB equals 1, 0, which means v is just in x direction. Right? So this dv is just the x direction, right? So it's the same as that. And it turned out that it's just a equals 1, b equals 0, so it's just fx. Okay? So in the simplest case that v is just an I, then you just get the fx, right? And the other way around, if it's 0, 1, then dy, right? Because, you know, v is along y direction, so it's the same as dy. Okay? But it could be something not along x or y. For example, along this 45-degree angle. There you have that. Okay, so this is the derivative along a vector. And we emphasize that this vector, in my case, it's an arbitrary vector. But if you're talking about a directional derivative, v must be a unit vector. If v is not a unit vector, then it's not a directional derivative. Because when you talk about direction, you must have a unit vector, right? Otherwise, for example, if I don't do, let's say here, if I don't do 1, 0, I do 10, 0, then this is 10 times fx. But that's kind of meaningless, right? What do you mean? You have a huge slope there? No. The slope will only make sense when you be a unit vector. Okay? So in this case, when I say the diagonal, it's not 1, 1, because the 1, 1 is not a unit vector. So how do I make a unit vector? I have to divide the vector by its own norm, own length. So what is that? What is the length of this vector? Yes. So when I say directional derivative, v has to be a unit vector. So this will become like that. And this will be the derivative along the diagonal direction. Okay? And let's see more examples. By the way, let me explain why this is the case. Say, suppose you start from here. You move a little bit along this direction. Right? Suppose you change by h. If you change by h in this direction, then how much do you need to change in x direction and y direction? If you make by this picture, if this is h, then how long is this? And how long is that? They're both h divided by square root of 2. Right? So how much does your z value change? From here to here. Well, you have to change it from here to here, then here to there. Right? When you change from here to here, it will change by fx times how long this is, which is h over root 2. Right? Then how much do you change from here to here? It's fy times h over root 2. That's the change from here to here. The z value. Right? Then you divide it by h. Then you can see the h will cancel, so you get this. Okay? So this is the explanation of why this is a directional derivative. Because that's how much the z value will change from here to here. Okay? So in general, if you have a point in space, this is fy, and ask you what is the directional derivative along this, then you need to tell me what is this theta. So this v would be cosine theta, sine theta. Right? Then the dv would be cosine theta times fx plus sine theta times fy. And if theta equals 0, then it's along x direction. If theta equals 90 degrees, then it's along the y direction. Yes?
Would you have to divide by the magnitude of that?
Because I choose cosine theta and sine theta, so the magnitude is already 1. You know, square of this plus square of that equals 1 automatically.
Oh, wow. Gotcha.
That's the good thing about the sine and cosine. Okay, so that's the direction. So if I give you a vector, I ask you what is the derivative along that direction. You have to normalize that vector first. If you're given an angle, then you can just write down the vector directly by cosine and sine. Okay? Let's say fxy equals x squared y. And what is the also 1, 2. Okay, here are two things. One is the value of x and y. The other is the direction. Okay, so don't confuse them. This is where you evaluate the function, and well, not just function, it's the derivative. Where you evaluate the derivative, this is the direction of the derivative. Okay, and because this is not a unit vector, we have to normalize it first. Okay. Then, how do you find out the direction of the derivative along that direction? You have to write out the first component times fx evaluated at this point plus the y derivative times the y component of the vector. Okay. All right. So what is the x derivative at that point? You have to take the derivative over x, so you get 2xy. Right. And I want the y derivative, it's just x squared. Then you have to plug in the values, x and y. X equals 1, y equals 2, so it's 2 times 2, we got 4. And this time x equals 1, y equals 2, so we get 1. Alright, so that's the directional derivative along that direction at that point. So you have to take derivatives over x and y, then times the corresponding component. Is that clear? Okay. Alright, now let's move on to 3D, which is pretty much the same. Say you have a fx, y, z. Then I can ask you about fx, fy, fg, etc. Right? I can also ask you about v, v, f. But now, what is v? V must be a vector in 3D with unit length. Right? Okay, let's try this example. So f equals x sine y z. Okay, so it's a function of 3 variables. And let's consider this point. 1, 3, 0. Because x equals 1, y equals 3, z equals 0. Okay, I'm going to ask you a few things. What is f at that point? That's even, right? You're plugging 1, 3, 0. What do you get? Just plug in 1, 3, 0. Yeah. 0. Yes, okay, 0, because sine 0 is 0. Very good. I'm not sure what is fx, fy, fz. What is fx?
Sine of yz.
Awesome. Sine yz. Great. Fy. X is no. If you take the derivative of sine,
It'd be cosine
then cosine yz
times z.
times z. Very nice. It's called chain rule. The last one.
X cosine yz.
Cosine yz times 1. Awesome. All right, then you plug in the value 1, 3, 0. Right? So at 1, 3, 0, fx, fy, fz. I write down in the form of a vector because I will tell you what's the meaning of that in a moment. But let's just put it that way first. So you get 3 values. What's the first value? 0. Second one,
B 0 again.
also 0 because v equals 0, right? The last one, oh, wait, not 0. Where's the last one?
Maybe 1.
No, 3, right? Because you have a y equals 3. Okay, so you have this 0, 0, 3. 3 numbers by putting it in a vector form. But let me tell you why I put it in a vector form. Remember what we say about the dv? I said it's v. Now, in this case, v has 3 components. I don't call them ABC, I call them v1. And then the fx plus v2 fy plus v3 fz, right? And do you notice this form is actually a dot product, right? Time, and add. So this can be written as v dot that vector, right? So it's particularly easy if you write down fx, y, fz, fx, fy, fz as this vector form. Then just take the dot product with your vector. And this one, which we wrote over there, is defined as, this is written nabla. You read it nabla, but we call this the gradient of f. So gradient is a vector that has as many components as the number of unknowns, number of variables. So if you have 3 variables, then the vector is in 3D space, and the 3 components would be the corresponding partial derivatives. Okay? So in this case, the vector would be 0, 0, 3 at that point, and in general, would be 3 components of this, and that. Okay? So, in terms of gradient, you can just say the directional derivative is v dot the gradient of f. Well, sometimes you can also write down this as a grad, but this is much easier to write, so I will use the triangular form instead of the grad form. Okay. So, let's finish this problem. So, I didn't even tell you what is v, right? Let me just give you v. So v equals, let's say, 1, 2, 1. And what is that? Well, take the derivative along that direction. To do that, you have to normalize it first. Okay, so you have to change this v to 1, 2, 1 over what?
Square root of 6.
Yes, very good. 1, 4, 1, square root of 6. Then you can plug in that formula. Whatever, here, 0, 0, 0. Okay? And what do you get? Let's look at square root of 6. That's pretty easy. So we have so many zeros. What's the dot product of a 1, 2, 1 and a 0, 0, 3? 3, right? So it's 1 times 0 is 0, 2 times 0 is 0, 1 times 0 is 3 is 6. So that's the answer. 3 over square root of 6. Alright? So that's your directional derivative and a gradient vector. Now let's see some geometrical meaning of this gradient vector. At each point, you have a gradient vector like here, right? If I choose my v, but let me go back to 2D. Okay, 2D is a little bit easier to visualize. say fx is equal to xy. And the gradient of f would be fx fy. Right? Suppose you have a a surface like that. Then every point you have a directional derivative. Sorry, not directional. You have a gradient. A gradient is like that. Okay, what is the geometrical meaning of this? Let's consider an fv. If v is orthogonal or perpendicular to the gradient f, okay, then what is directional derivative? It will be v dot that, right? And what is v dot that if they are perpendicular? Zero, right? The inner product will be, the dot product will be zero. And what does that mean? It means f is not changing along v direction. Okay? So it means I'm moving along this contour line. You see that? So it means v must be along this contour line because f is not changing. So if I plot this 3D picture in the contour plot, like that, then you can see this must be the direction of v that is perpendicular to gradient of f. Right? Because along this v direction, f is not changing. So this curve corresponds to that curve. Okay? So what is the gradient of f in this picture? It must be perpendicular to that. Well, you can draw very well, like that, right? And in other words, if you move along this direction, then you are either ascending fast or descending fast, depending on which direction you go. Right? The gradient tells you the climbing direction or the descending direction. If you are walking perpendicular to the gradient, then you are moving horizontally. On a plot, okay. For the function, it means the function value is not changing. And this gradient direction is the direction along which the function changes fastest. Okay? I can also prove it more rigorously. Right? The direction derivative would be this. And this is a dot product. Remember the formula relating the length of these two vectors with the angle between them? This equals the length of vector 1 times the length of vector 2 times the cosine of angle between them. The angle is not for v, it's between them. Okay? So like this is v, this is gradient of f, angle between them. Remember this formula? Right? So this tells us that, well, because v is a unit vector, so this is just 1. Right? So this tells us that the directional derivative has a maximum value when theta equals 0. Right? When theta equals 0, cosine theta equals 1. So this is the maximum value. And when do we achieve this maximum value? If v is along the gradient of f. So it means if your direction is chosen to be along the gradient, then the directional derivative is the largest. And if you choose the opposite way, then the theta would be theta would be 180 pi. So the cosine theta would be -1, which means you are moving in the opposite direction of the uphill direction, you are going downhill. So this will be negative of the absolute value of gradient of f. Okay. And if you are moving halfway, then this is cosine half pi, which is 0. So f would be a constant along this direction. Right, so it's very clear when you visualize here. If you're moving in this direction, you're climbing. If you're opposite way, it's deep. And going downhill, if perpendicular, then it's horizontal. Okay, so this gradient of f tells you the direction of the uphill. Or you can say the steepest uphill direction. Because we can say this is also uphill, but that's the fastest. Okay, so when you look at a mountain, there's the one direction that is steepest, and that is the gradient of f. Okay. All right, when you go to 3D, it's more hard to visualize, but you can still call it that way. Say if you have a fxyz, then what is this gradient f represent? It still represents the direction along which the function is increasing fastest. If you are moving in the opposite direction of that, then you are decreasing, the function will decrease fastest. If you are moving in any direction that is perpendicular to this, which is not one line, because this is in 3D, so there's a plane. Anywhere in this plane, then you get f is constant. So that gives you the contour surface. If you plot this function in 3D, that's impossible, right? In 3D, you can only plot the contour surface. So similar, when you have a gradient, it always point in a direction where the function increases fastest. Okay. And because of that, we can say, we can tell the level surface of this. The level surface. Is this equal to constant? It's like a contour plot, but this time it's each constant would be a surface, not a curve, right? Not like a circle or something. It'll be more like an ellipse kind of another ellipse, like a sphere kind of a surface. Then for every point along this level surface, I can, have a 3D thing, right? I can say there is a tangent plane. Right? Suppose you have this is a deformed sphere. Then there's a tangent plane to the surface at every point. Can you tell me what is the direction? What is the equation for this tangent surface? Say I ask you to imagine this. This is a tangent. Sorry, this is a surface. Right? It's a relation between x, y, z. So it's a surface. It implicitly defines z as a function of x and y. So it's a surface. Since it's a surface, we can talk about the tangent plane to that surface at every point. So can you write down the equation for this tangent surface? Well, it sounds hard, but let me tell you how. To determine this tangent plane, you need to know two things. One, a point on the plane, which is, of course, you know, because you know it's passing through the point you're given. Right? Second, you need to know the direction of the plane. But what does the direction of the plane mean? Plane is not a line. The direction of the plane means the perpendicular or the normal direction of the plane. Right? And what is the normal direction of the plane? Can you tell me? It's right there. Why? Because all of these directions in the plane, right? So it's not just two lines, it's also perpendicular to that. All of these directions, along these directions, f is constant. Right? And this direction is perpendicular to all of this. So what is that? It must be the gradient. Because along the gradient, the function changes fastest. And perpendicular to the gradient, the function is not changing. And this is what happens. Along this direction, the function stays there, so it's not changing. So the normal direction of the tangent plane is exactly the gradient. Okay? Let's see an example so you can understand this better. The simplest one. Because the level surface is, what does this represent?
sphere?
Yes, very good. It's a sphere, right? Okay. So I'll give it a point on the surface and ask you what is the tangent plane. Well, then you need to know the normal direction, right? Because the sphere is very clear. The normal direction is just this, right? Starting from the center, point in that direction. And is that given by the gradient of this vector? Yes, because what is the gradient of this? If the 6x, y, z derivative, what do you get?
X.
2x, 2y, 2z. Right? And because for direction, this needs to be normalized, so these two doesn't matter. Just pointing in the direction of x, y, z, which means from origin to x, y, z, so it's just that. Right? So you can see that the normal direction is indeed given by the gradient of this function in this simple case. Okay? The tangent plane would be like that, right? And the normal direction of the plane is given by that. Now I'll give you more examples. So if I write out in equation form, that's, let's say I call this point. So let me make it more concrete. Say I call this, let's say 9. And I fix a point on it, 1, 2, 2. All right, 1, 2, 2 is on this sphere of radius 3. Right? So I ask you to write down the equation for the tangent plane. Then it's just this. You take its directional, you take its gradient at that point, you get the normal direction. Right? And what is the equation for the plane? It's just this. If you remember, that's how we write on a plane. Norm times this R naught in the plane, point on the plane, and n is the normal direction. Right? The geometrical meaning is that the difference between any point in the plane and a fixed point in the plane give you a vector in the plane. Right? And the vector in the plane is perpendicular to the normal direction. That's how we write out the equation for the plane. In this case, the normal direction is given by this gradient, and R naught is just this 1, 2, 2. Okay? And because this 0 on the right hand side, we don't need to normalize n. Because normalize means divided by a constant, right? Because it's 0, so it doesn't matter. So you can just plug in this gradient directly. Okay? So it just means take its gradient, 2x, 2y, 2z, then plug in 1, 2, 2. What do you get? You get 2, 4, 4. Right? Then you take the difference between R and R naught. R is x, y, z. This is 1, 1, 2, 2. So that's the equation for the plane. And if you expand it, it says 2x minus 1 plus 4, y minus 2 plus z. Plus 4, z minus 2 equals 0. Okay, so that's the equation for the plane. So the three coefficients are just in the normal direction given by the gradient. And the three number to subtract is just the starting point of your tangent plane. Okay?
Can you go over again what exactly? So it's the gradient on the second line.
Okay. The first one tells you how to write an equation for the plane. For any plane. You write in a normal direction. You figure out the normal direction. and you're given a point in a plane. Right? Then that's the equation for the plane. Here, n and r naught are constants. R is the xyz in your equation. Okay? And then in our particular problem, we want to find out the tangent plane. So our r naught is given because you know the point. Then what is the normal direction? It's given by the gradient of the function at that point. Okay? Then you just plug in numbers and then do the calculation. You can regard this as an application of the gradient vector. Well, of course, the gradient vector is very useful, but for now, let's just say this is our application. So I ask you this problem as one example. Okay, this is an equation for a surface. Can you imagine what kind of surface?
It's a 3D ellipse. I don't know.
Yes, exactly. Actually, it's the name for that. It's not ellipse, it's called an ellipsoid, which exactly means 3D ellipse. So it's a 3D ellipse, because you can see if you don't have the 4 and 9, it's just a sphere, right? If you have 4, you have to stretch x direction by 2 and y direction, z direction by 3. So it's an ellipsoid that has something like that, right? So this is a surface, because it equals 3, right? So we're talking about surface. So let me pick a point on it. Well, the easiest one to pick is this, 2, 1, 3. Right, because 2, 1, 3 is on this surface. Getting 1 plus 1 plus 1. So let's find out the equation for the tangent plane. Okay, then let's set over there, just plug in the equation. The equation says the normal direction is given by the gradient of the function. Well, you say the function equals left hand side or minus 3, doesn't matter because minus 3 will give you a 0 as a gradient. As derivative. So you can just say the left hand side. Okay. So the gradient at that point, otherwise it's not a number, it's a function, right? You have to get a number, a vector, then you times that. All right, let's take it. So what's the derivative? What's the x derivative? I mean, come on.
1/2 x.
1/2 x, great, and then
2y.
2y, and then
2z.
2z, yes, 2z/9. Then you have to do something before you go on. You have to evaluate at 2, 1, 3. Right? So let me put it in 2 steps. Let me call this n. So let's figure out n first. Then I plug in there. Okay. Otherwise you have a kind of long formula. So plug in these numbers, what do you get? 1, 2, and then two. Okay, then my equation is filled in. Ready? 1, 2, 2/3 dot x minus what?
Bx minus 2?
Yes, y minus 1 and z minus 3. Okay? So that's your equation. Well, if you want, you can expand it x minus 2 plus 2, y minus 1 plus 2 thirds, z minus 3 equals 0. Right, that's the equation for the plane. Well, here are more examples. So you have a two variable function like that. And I give you 2 points. 2, 8. 5, 4. What is the directional derivative at 2, 8 along this direction? So the derivative of f at 2, 8 along v. V is this. So this time you are given a point where you take a derivative, and the direction is given as a segment between two vectors. Sorry, between 2 points. The vector between 2 points. So you need to figure out v first. Right? What is v?
3, negative 4.
3, negative 4. Very good. Right? But to use this v in a directional derivative, you have to normalize it first. Right? So what is directional derivative? We have to write down v with normalization. So what is that?
Divided by 5.
Very nice. Then I can just write down the remaining part as a gradient, right? Because the direction derivative now, from what we already learned, it is the vector, the normal vector, unit vector, the unit vector times the directional derivative, times the gradient. Okay, what is the gradient? You have to take the derivative along x and along y, right? Then evaluate at this point. So what is the x derivative?
1/2 y to the negative
1/2 square root of y is still there, but square root of x becomes the denominator, right? And this one is the other way around, square x, square root of y. Yes? Then have to evaluate this at 2, 8. Okay, plugging 2 and 8, what do you see? Square root of 8 over 2, that is 2, right? So 2 cancel the 2, you get 1. And then this times 2 over 8, which is 1 over 4, and then the square root gives you 1/2. 1/2 times that equals 1/4. Right? Then what do you get?
V 3/5 times 3/5
3 minus 1. You need to do the dot product,
Okay.
right? 3 minus 1. So you get 2.
2/5.
Yes.
Do you usually bring out so you normalize that you divide by 5. Do you usually bring out what you normalize by when you do the dot product?
Yes, because it's a division for every number, so it's easiest to leave it to the end.
Okay.
Otherwise, you have to do 3/5 and 4/5. That's just extra work. one more problem. Oops, okay, suppose you're given this function, which is a two-variable function. And let's consider the point 1, 0. Okay, what is the function value at that point? Zero, right? Sine 0. What is the fastest rate change, the maximum rate change, and in which direction? Okay, let me say it more clearly. So if you take the derivative along x direction, you get the slope along x direction, right? But if you take the derivative along y direction, you get probably a different slope. I'm asking you which direction will give you the largest slope, and what is that slope? Okay, so if you plot this function, it will be a surface. At this point, you can find out direction where the function grows fastest, and how fast it grows. Or you can say what is the slope, and what is the direction. Do you have to do that? Well, from the geometrical interpretation of the gradient we talked about, the fastest direction is given by this. And the fastest slope is just the gradient, it's not. Remember, this, right? Then we say this is and this v is a unit vector. So when is this largest? When cosine theta equals 1. So this is the largest value. And which direction will give you the largest slope? When v is parallel to the gradient of f. Okay, so the gradient can tell you both the direction and the maximum slope. All right, so let's find out what is the gradient. Takes x derivative, you get a cosine xy times y, right? Then the derivative of y direction is cosine xy times x. Then have to evaluate at 1, 0. What do you get? The cosine part will give you 1 because cosine 0 equals 1. So you just plug in y equals 0 and x equals 1. So that's a gradient. Gradient at this point. Okay, what does that mean? What is the direction where you have the largest slope? It's given by this vector, right? Where does this vector point to? Come on, this vector is very simple. Yeah, you can say up, but it's better to say it's in the y direction, right? So it means the derivative along y is the largest among all the directions. Okay? And what is that derivative? Well, it's just the derivative along y, right? Well, in this case, because this is a unit vector, so it's just 1. The largest slope is given by this. So it's 1. So if you plot this function, you will see along x direction it's horizontal. Along y direction it's like that. And the slope is 1. Okay? Well, that's it for today. We'll continue next time.